Early in the 20th century, Einar Hertzsprung and Henry Russell independently created diagrams in which stars are plotted according to their absolute visual magnitude and their spectral type. This is a typical Hertzsprung-Russell diagram, which clearly shows a distribution that is not random. The majority of all stars plotted sit on this belt running across from the top left down to the bottom right. This is known as the main sequence. A main sequence star has reached a stable hydrostatic equilibrium state. Our Sun is a good example and sits here on the main sequence. There is a definite grouping in the top right of the diagram where we find giant stars, with white dwarf stars grouped on the bottom left. The ability to launch satellites into space has provided crucial insight into the life of stars. Protostars form from collapsing gas clouds. On the Hertzsprung-Russell diagram, these infant stars do not appear on the main sequence curve, but take a path known as the Hayashi track as they progress towards the main sequence. Once a protostar becomes a fully fledged star, we find that its position on the main sequence line depends upon its mass.
The famous constellation of Orion, the Hunter. Here we find a giant molecular cloud stretching from Orion's belt to his sword. Visible to the naked eye is an area of this cloud known as M42, the Orion Nebula, an exquisite sight when viewed in visible light. M42 is visible because of young, very hot stars that have formed here, exciting the surrounding hydrogen gas, which glows in the visible part of the electromagnetic spectrum. But using visible light, it is not possible to look inside this beautiful nebula. The gas and dust it contains blocks the view. To explore M42 further, astronomers need to detect longer wavelength electromagnetic radiation, which can pass through the gas and dust. An infrared telescope unveils M42, providing a glimpse of forming stars. It is not only protostars that are found in the Orion Nebula, it also contains a cluster of very young stars. Observation of X-ray emissions from the Orion Nebula have enabled astronomers to discover more about the behavior of Sun-like stars that are just 1 to 10 million years old. These young stars release violent flares that are more energetic and occur more frequently than any seen from our middle-aged Sun.
At the other extremity, a star that is more than 8 times the mass of the Sun evolves from the main sequence on the Hertzsprung-Russell diagram to the region of the supergiants. These massive stars have an explosive end to life, a supernova. M1, or the Crab Nebula, is located in the constellation of Taurus, but is not visible to the naked eye. This intricate, striking nebula is the remnant of a supernova that was so bright it was visible to the naked eye in 1054 AD and recorded by Chinese astronomers of the time.
It's another beautiful nebula in the visible spectrum. Images of the infrared radiation emitted by M1 reveal filament structures that run through this nebula. These are thought to contain hot gases, but their exact nature still remains a mystery. The infrared also shows a cloud of energetic electrons trapped in a magnetic field and emitting synchrotron radiation. What is driving this cloud of electrons is exposed when X-rays emitted by M1 are detected. At the heart of the Crab Nebula, we find the leftovers of the original star, a rapidly spinning neutron star. This pulsar has a mass equivalent to squeezing the Sun into a ball just 20 kilometers across. It is rapidly spinning and spewing out pulses of high-energy radiation 30 times a second. Detecting high-energy X-rays that are emitted from the fast-moving particles in the center of the Crab Nebula allows astronomers to probe deeper into this exotic object.
However, there is much more to these objects than just a pretty picture. After detecting radiation from space, astronomers need to analyze it to uncover clues to help reveal the physical processes occurring inside. One way is to study the spectra of light. This provides astronomers with specific information about the makeup of an object. All chemical elements have their own characteristic signature due to the absorption and emission of light at a particular wavelength. This is not just limited to the visible wavelengths. The unique signatures of different elements can be found right across the electromagnetic spectrum, providing crucial information about the chemical composition of celestial objects. Over the last half a century, scores of satellites have been launched to detect radiation across the entire electromagnetic spectrum. We have explored why spacecraft are needed to study the universe, and a little of what they can tell us. There is so much more to understand, and as technology develops, even more advanced detectors will be launched, permitting astronomers to solve the remaining mysteries of the cosmos. I'm Rebecca Barnes. Thank you for watching the first Science at ESA vodcast.